Three-phase SCIM motor calculations. In this presentation, we're going to be looking at some calculations to do with three-phase motors that are torque related, speed related, and we're also going to introduce a concept referred to as percent slip. Well, let's get going. The first thing we need to know is that torque is really rotational force. If I were to turn this object here, and let's imagine it's a bar and I'm looking at the end of it, or the motor shaft, and I grip it and I twist it, I'm applying torque. Now, obviously there's different values of torque. If this is connected to a motor and there is nothing else, and I simply take the shaft and I spin it, well, it doesn't take much torque for me to turn a motor shaft that's not energized and it's not driving anything. So that takes very little torque. However, if this motor shaft was connected to an extremely large metal flywheel that was stainless steel and it was like 15 inches thick, and I took my hand on the shaft of the motor and I tried to turn it or twist it, it would take an immense amount of torque for me to slowly start to get that item moving from its stationary position. So torque is something that we can calculate on a motor, and it's symbolized with the letter T when we have equations, and it's measured in two different forms. There's actually a few more, but we won't get into those. Torque has to do with distance and force, and so the way it's measured is in those two metrics: newtons, that would be force, and meters, well, that would be distance. Down here, imperial, foot-pounds of torque. Why do they reverse the distance and the measurement of the force? I have no idea. Imperial never makes sense. And as long as you remember that, everything is okay. All right, so let's take a look at the equations that are utilized in order for us to calculate torque in those two different variations. The first one we're going to look at is metric. Yes, we need to know how to do both, because outside North America, metric is king. In North America, imperial, for some reason, still reigns supreme. So metric torque is equal to the power out. What is power out? Well, power out is the watts at the shaft of the motor. This is mechanical watts. And remember, we can convert horsepower to watts by multiplying the horsepower by 746. We then take this value and multiply it by 9.55. This is a constant value. It does not change. It is utilized whenever we want to calculate torque in metric. Then we divide it by the RPM. How quickly is the rotor turning? And that will give us our answer in Newton meters. On the flip side, imperial land, torque is equal to the horsepower, which is the power out, multiplied by 5252. And again, this is a standard constant value that is used every time we want to calculate imperial torque. We then divide it by the RPM of the rotor, and we end up with the torque value in foot-pounds. So the horsepower is at shaft of the motor, the torque comes out in foot-pounds, and on metric, we have Newton meters for torque, and the power out is simply the horsepower multiplied by 746. All right, well, let's take a look at an example that utilizes this type of calculation. This first one is a 15 horsepower motor that's turning at 1735 RPM. With only this information, we can calculate the torque. The first calculation I'm going to do is metric. And with metric torque, we know that we first need to take the horsepower and multiply it by 746. This is my power out. I'm then going to take those values and place them into my equation. And at this point, yes, we now have a torque value of 61.59 Newton meters. If we were to calculate this value in imperial, well, then it's actually a little bit shorter path in the calculation. All we do is take our 15 times 5252, divide the whole thing by 1735, and we end up with 45.4 foot-pounds. Well, let's try that again. Let's calculate the two different values of torque with imperial or metric. So I'm going to start with the imperial this time just to mix things up. So there's imperial, 30 horsepower motor turning 1200 RPM. Let's calculate the torque. Well, 30 times 5252 divided by 1200 gives me 131.3 foot-pounds of torque. Whereas on the imperial, or the metric side rather, When I have 30 times 746, it gives me 22,380 watts. That's the power out. And we slap it into our equation. 22,380 times 9.55 divided by 1200 equals 178.1 Newton meters. All right, well, let's take a look at another topic then. This topic we're going to look at is speed. Now, we're talking about the speed of the rotor, and the speed of the rotor is symbolized in N. And I should paraphrase that. It's not always speed of the rotor, it's just speed in general. It's symbolized with the letter N when we have an equation, and it's measured in RPM. That's revolutions per minute. And what that means is how many times does the circular object turn in a full 360 mechanical degrees every minute. All right, well, there's a few different types of speed that we need to be aware of. And those different types of speed have to do with where they are going to be measured. Now, the first one is the speed of the stator magnetic field. This is referred to as synchronous speed, and it's represented in an equation as N sync. Now, this is a little bit odd because it's not actually speed that you could watch. It's invisible speed. And what I mean by that is it is the relative speed of the magnetic field that's rotating caused by the stator. So it's a magnetic field speed. Now, this is utilized because we know that the magnetic field speed of the stator is going to have a direct relationship to the rotor. The rotor gets pulled and pushed along by the stator, and that means that this, well, is going to be somehow based on this. So we have two different speeds, the synchronous speed, which is magnetic field speed, and then we have the rotor speed, which is the mechanical rotational speed of the rotor itself, and that's N of the rotor. Now, it's important to understand that the synchronous speed will remain constant and be unaffected by mechanical load. So this is purely based on a couple of different factors that we're going to calculate. The rotor speed is always slower than the synchronous, and it is affected by the mechanical load. And so this is one that will vary in speed depending on what we connect to the motor. Well, let's take a look at a few of the equations that we're going to utilize to calculate synchronous speed. And synchronous speed is the magnetic field speed, and it's calculated from the number of magnetic poles per phase inside the motor plus the frequency of the AC that is being applied. So there's two different equations. This is the first one. N synchronous is equal to 60 times the hertz divided by the total pairs of poles per phase. Now, there is a second equation, and I show it simply because some people will see this equation in different areas, different textbooks from their friend, who knows. Notice how similar they are, and also notice the one difference. This one is counting the total poles per phase that are inside the stator. And don't worry, we're going to take a look at what those poles actually look like and how they're arranged. This one's looking at the pairs of poles. Pairs, pair of shoes, two to a pair. Notice the multiplier, 60 and 120. Slightly different. Notice I put the word or, which means I don't care which one you use, nor does anyone else, because they both give exactly the same answer. So what are they referring to when they say pairs of poles or poles in general? Well, here's a diagram with three different motors. And these three different motors have a stator that is constructed a little bit different. This one here, I've colored them. A is red, C is blue, B is black. You'll notice there is 1, 2 poles. And the pole is the metal item that concentrates the magnetic lines of flux right on the surface here. So they pass between these two, and that is the A phase. So we can see here, A1, A2, this is one pair of poles, 2 per phase. Over here, we have 4 poles, and that would mean there are 2 pairs of poles per phase. We got 1, 2, 3, 4. And over here is a 6-pole machine, and this one means we have 3 pairs of poles per phase. So I got 1, 2, 3, 4, 5, 6. So this has a direct relationship with the speed of the motor, depending on how many pairs of poles I have constructed in the motor itself. Now, obviously, this is not going to be changed by the electrician. However, the other factor that affects the speed of the motor is the frequency. So here's 60 hertz, and here's 160 hertz. Notice that the voltage or the amplitude of the positive and the negative alternation is approximately the same. The voltage being applied is the same. However, the hertz has changed. And remember, the hertz that's applied to the stator is going to affect the speed of the rotor. If I apply a higher hertz, it means that it's going to go through that 360-degree electrical degrees more times in a set time period. So, a couple of different things that affect the speed of the motor. And we'll discuss these in more depth as we go along. Well, let's take a look at a few examples now. All right, so we're going to calculate the synchronous speed of a couple of different motors. The first one we're going to look at is this one. This is a SCIM motor, and it has 4 pairs of poles per phase and operates at 60 hertz. What is the synchronous speed? Well, all we do is plug in the values, and like I said before, it really does not matter which of those two equations you utilize. I'm choosing to use the one with the 60 multiplier, which means I'm counting the number of pairs. Second question, 1 pair of poles per phase and 50 hertz. What's the synchronous speed? Well, 60 times 50 divided by 1 gives me 3,000 RPM. And finally, SCIM motor, 6 total poles per phase, 60 hertz. What is the synchronous speed? Well, 60 times 60 divided by 3 gives me 1,200 RPM. So that calculation is pretty straightforward. Let's talk about the rotor speed. The rotor speed is the mechanical speed. It's no longer a fictitious sort of in the air electromagnetic flux speed. The rotational speed of the rotor is determined by the mechanical load applied to it. In a SCIM motor, the rotor speed is always slower than the synchronous speed, always. And the difference between the two speeds is called the slip. So remember, the rotor will not turn at the same speed as the stator, and since they are operating at different speeds, there must be a difference between the two. So one's operating at 1800, one's operating at 1700, subtract the two, you'd end up with 100 RPM. That would be the slip. So in synchronous minus the rotor speed equals the slip speed. So this equation can be utilized either form. We could calculate for synchronous, rotor, or slip, and it's simply just a subtractive equation. So you should be able to manipulate it quite easily without too much trouble. Well, let's do a couple of examples that utilize this equation in all 3 of those calculated variations. The first one is I have a SCIM motor, and it has a synchronous speed of 3,600 RPM and a rotor speed of 3,250. What is the end slip or the slip speed? Well, we simply take 3,600 minus 3,450, and we end up with a 150 RPM. That would be the slip speed. The second question, SCIM motor, it has a slip of 150 and a rotor speed of 1,650. What is the synchronous speed? Well, in this situation, all we're doing is manipulating that equation, so it's 150 plus 1,650, 1,800 RPM. And finally, we have a motor that has a synchronous speed of 900 and a slip of 36 RPM. How fast is the rotor actually going? Well, in this situation, we'd simply take 900 and subtract 36 from it, giving us 864. So we've calculated what the synchronous value is. We've calculated what the rotor speed is and the slip. Now there's more terms that go along with this, and that has to do with percentages. So let's take a look at how we actually or typically express or describe this difference of speed. So how much slip a rotor is exhibiting is often expressed as a percent. Percent slip is equal to the slip speed divided by the synchronous speed. And so as an example, a motor with a slip of 20 RPM and a synchronous speed of 1800 RPM, we would say is operating at 1.11% slip. Now, percent slip has some pretty common values that we should have in the back of our heads. And so I'm going to give you a few common percent slip values that we should be aware of. The first one is, what is the typical percent slip for a motor that's operating at full load? Well, at full load, most motors operate between 3 to 5% slip, not very much. What about a motor that is not operating with any load? So no mechanical load. Well, if the motor's operating with no mechanical load, it is going to turn a little bit faster. And because of that, or due to this, the percent slip will actually reduce. So a motor that's running at no load will be from 1 to 3% slip. And finally, a stationary motor or a motor at start, the instant you start it, or if you took the shaft of the motor and you gripped it so that it couldn't move, we would say that's 100% slip. And that's because the rotor isn't moving and the synchronous speed is at its constant value. So, how consistent a motor's rotor speed from no load to full load is called its percent speed regulation. So this is slightly different than the previous percentage we have just looked at. The previous one was simply saying, what's the percent slip? This one is saying, how good is the motor at keeping a consistent speed from no mechanical load to full mechanical load? And the way that we're going to do this is we're going to be using information about the rotor speed when the motor is running with no load and the speed of the rotor when it is under full load. So here's an example of motor A. Motor A at no mechanical load is 1799 RPM. Under full load, and this would be the load right here, it is the mechanical load that the motor is rated for, it's its nameplate equivalent load, and you can see the speed drops. The speed at full load is 1735. This would be seen as a good motor, and the reason I say that is because the difference between these two speeds is actually quite minimal, as in it's able to regulate the speed fairly well from no load to full load. On the flip side, we have a crappy motor over here. Now the crappy motor at no load has about the same speed, 1799. However, if I were to connect the crappy motor to the exact same rated load, so just imagine for me that these are exactly the same size windmills, at full load, it drops down to 1321 RPM. This one does not do a good job at regulating its speed from no load to full load. So we can calculate what the percent speed regulation is for both of these different motors. Let's take a look at the calculation and how it is done. So speed regulation is the difference between the no load and the full load speed divided by the full load speed times 100. So remember, the speed at full load is always the motor's nameplate RPM rating. That would be what the manufacturer states it should be able to turn at when you have a rated mechanical load connected to the shaft. So here's motor A. We've got a SCIM motor with a no load speed of 1799 RPM and a full load speed of 1735. What is the percent speed regulation? Well, for this motor, all we're going to do is take the two values, the no load, and subtract from it the full load. We end up with 64 RPM. That's the difference between the two. 64 divided by 1735, that is the full load speed, equals 0.036. To make it into a percent, we always multiply by 100, and we end up with 3.6% speed regulation. This is considered good. Let's look at the second example. That was the crappy motor, and the crappy motor had a no load speed of 1799, but then a full load speed of 1321. What is the percent speed regulation? Well, in this situation, when we subtract the two, we end up with 478 RPM as the difference between the two speed values. And when we stick it into our equation, 478 divided by 1321, well, 0.361 times 100, 36.18%. This is considered very poor speed regulation. Remember, it's advantageous or helpful or better or best, or it's really desired that the motor's speed from no load to full load is consistent and close. You don't want a massive variation between those two values. And that brings us to the end of all of the different three-phase SCIM calculations for three-phase motors.